Hi, everyone. Welcome to another episode in what we have learnt from A New Kind of Science. So A New Kind of Science, the book, that's this big thing here, came out 20 years ago. In May, it will be 20 years. And I am going through every week talking about successive chapters in this book. And this week, I'm on chapter 3, which is called The World of Simple Programs. Chapter 3 was a chapter that I wrote most of. It was kind of the launching chapter for many of the discoveries in New Kind of Science. I had worked in the 1980s on simple programs called Cellular Automata, which I talked about a bunch last week and which are the subject of chapter 2 of the book. And I had discovered this remarkable phenomenon that even when the rules by which the program operates are simple, the behavior of the program can be very far from simple. So one of the big questions that I wanted to address when I had the opportunity to start working on New Kind of Science was, how general is that phenomenon? I should explain that in the early 1980s, I worked on Cellular Automata. In 1986, I kind of turned to working on tool building and started building what became Mathematica and Wolfram Language, and started our company, Wolfram Research, right around that time. First version of Mathematica was released in 1988. And for a little while, I was kind of involved in, all of my time was taken kind of developing version 2 of Mathematica and developing our early stages of our company. But in 1991, I decided that I was perhaps injecting even more new ideas into the company of the size we had than it could possibly withstand at the time. So I should throttle back on that and go and actually use the tools that we built to try and explore things in science, and in particular to try and follow up on the kind of discoveries I'd made in the computational universe in the 1980s. And so I went off. I physically removed myself from Illinois, where our company was headquartered, and I was in California. And I thought it would be like a year and a half of let me just explore a few things and write something about them. Turned out to be 10.5 years, because I discovered a lot more than I ever expected to discover. Only was in California for like a year and a half, but I think during that period of time was a lot of when I worked on chapter 3 in the book and tried to answer this question: out in the computational universe of possible simple programs, how general is this phenomenon that I'd found in Cellular Automata, where simple rules can produce complicated behavior? And at the time, the primary computer that I was using a Next computer. That was my primary system, the Unix-based system that had a nice graphical user interface. I was kind of running lots of the programs that were what contributed to chapter 3 of the book, were things that actually I ran on networks of up to a few hundred computers at our company, trying to explore different kinds of things that I'll show you a little bit of. So kind of the big question was, out in the universe of possible simple programs, what kind of behavior do you typically see? So that was the subject of chapter 3. And let me give you a little bit of, show you a little bit more about what was going on there. So here we go. We talked in previous weeks about the foundations for a new kind of science, kind of the underpinnings of the approach that I was using, about the crucial experiment, discovering that even in simple cellular automata like Rule 30, it's possible to go from a very simple rule and very simple initial conditions to very complicated behavior. So how general is that phenomenon? So that was what I launched on in chapter 3. And I should say that as I worked on chapter 3 in 1991, 1992, that was kind of when I formulated this thing that I now call the principle of computational equivalence, which I view as being one of the most important general principles across theoretical science. And it's what has ultimately led to many of the things that I've done, including now our physics project and the extensions of that into mathematics and beyond. So in a sense, chapter 3 was the empirical raw material necessary to discover the principle of computational equivalence. So the first thing I did in chapter 3 was just say, okay, I've looked at particular cellular automata in chapter 2. What what's the more general story? And the first thing I had to do here was to introduce how do you specify a cellular automaton? Very simple. There's this numbering scheme that I had invented in the early 1980s, where you just take, let's say in this case, you take all the possible configurations of the neighborhood of cells around a given cell, a cell and its left and right neighbors, and you say for each of those possible configurations of the neighborhood, what will be the value of the center cell on the next step? And you say that and you just write down those numbers as base 2 digits, and then you convert that base 2 sequence to decimal, and that gives you the number. So rule 30 is the 11110 is in that as a base 2 number is 30 in decimal, and so that's kind of the numbering scheme. So that means that given that there are 8 possible values here, there are 2 to the 8 possible cellular automata that I called the elementary cellular automata long ago. The first question was, what do they all do? So this is a sample of a few of them, rule 100 through rule 139. And you can see that some of them do very simple things. You just start them off with one black cell in the middle and it just keeps going. Some of them do more complicated things, make these nested patterns and so on. This is a reflection and inversion of my favorite rule 30. That's rule 135 there. So the first question is, what do all the 256 possible cellular automata do? And this was a 2-page spread of kind of the story of the elementary cellular automata. I view it as a little bit like a sort of a periodic table of the elements, except that this is kind of the complete collection of possible rules of this type. I had always intended to make kind of a wall chart of these things, like these tables of elements. Just like with tables of elements, you can start describing, well, what is this element? What is tantalum used for? What is rhenium used for? And so on. It's turned out over the years since I first introduced these elementary cellular automata back in the early 80s that different rules here have been used for all sorts of different purposes. And you could kind of go down and say, this one is a model of catalysis. This one is a model of road traffic flow. This one is a model of formation of patterns on pigmentation patterns on animals and so on. And I've always thought it would be amusing to make that sort of chart that talks about the sort of foundational kind of the foundational science of this together with its applications. Now, it's become a lot easier in intervening years to make this picture. So, for example, now if I just go to a Wolfram notebook here, I can just start saying, make a table of, and I seem to do this so many times, and when I give talks about different kinds of things, I'm making this picture. It's kind of like you start off from an arbitrary rule and the nth rule, and you go, let's say, 40 steps, and we say that all is to tell it to show us the complete region of the cellular automaton, even if the actual cellular automaton doesn't really make use of all those cells. So here now is the version of that picture that I had over there on the right. There are all the various elementary cellular automata in all their glory, so to speak. I'm urged to just make a version of that picture that really that really kind of shows the things at a smaller scale here. I'm just want to make my postage stamps of the elementary cellular automata. There they go. And you can see there's sort of a distribution of behaviors from these ones which are where the most dominant feature is stripes. That's caused by the fact that the 0, 0, these are the odd numbered rules. So the rules end in 1. So that means that the 0, 0, 0 configuration turns into 1, which means that the thing that starts as all zeros here turns into 1s, and you get the striping behavior. We'll see that in many cases we don't have growth, but sometimes we do. And so what I did in here was I start talking about the different kinds of things that can happen. What percentage of patterns do this or that? So this is the collection of sort of distinct nested patterns that you get from the elementary cellular automata. The kind of the simplest is what you see first in rule 22, but it's really its type specimen in the biological sense is really rule 90, which is the rule that you get by just saying the value of a cell is the sum mod 2 of the values of its left and right neighbors. So it's Pascal's triangle mod 2. And it turns out that Pascal's triangle mod 2 makes this nested pattern, the Sierpinski gasket, that has a fractal dimension log to the base 3 of 2. And you can kind of see that by seeing that in any given region here, you're just taking sort of, there are 3 pieces. If the thing was going to be of dimension 2, with every time you look at a little region here, you would see that all 4 pieces that would sort of fit in this region are there. But actually, it's only 3 of those pieces. And that's what leads to this thing not being of sort of full dimension of an integer dimension, but being of a fractional dimension, in this particular case, log to the base 2 of 3, which is about 1.69 here. 1.58. That's 1.58. The other case, there are a couple of cases that are distinctly different. One of them is Rule 150. Rule 150 is what you get by taking not the binomial coefficients mod 2, but the trinomial coefficients. That's the expansions of 1 plus x squared to the power n. The coefficients there are the trinomial coefficients, and those mod 2 produce this pattern here. This pattern here has a kind of a double nesting. This is kind of like a one-level iteration nesting. This is 2 levels of iteration, and it actually makes it's kind of like a Fibonacci sequence where f of n is f of n minus 1 plus f of n minus 2. This has that kind of 2-level nesting, and the result is that its fractal dimension is actually deeply related to the Fibonacci numbers. It's actually given by log to the base 2 of 1 plus square root of 5. It's related to the golden ratio, which is the ratio of Fibonacci numbers, and that's because it has this kind of double recursion thing going on. Now, I should emphasize in NKS, in the book, I have the notes are a very important part of the book, it's let me just look here at notes for this section. I just want to show you a few of the other ones. Let's see, we talk here about, there are different possible orderings you could use, but I also was going to show you, these are sort of typical algebraic forms for these rules. These rules you can state just as a kind of table of what happens in each case, but they also can be represented like here's rule 150 is P plus Q plus R mod 2. Or rule 60 is just P plus Q on one side, mod 2. Rule 90 would be P plus R mod 2, and so on. Some of these other rules, as I mentioned last time, rule 30 is almost just like that, but it has one little piece of nonlinearity, and so does rule 22. But rule 22, as we'll see, doesn't, its nonlinearity doesn't get in the way, at least when it's just starting from the a single black cell as its initial condition. Now, what I was going to show you here, let's see, here we go. So this is, so you can represent every cellular automaton rule as a Boolean expression. Like, for example, rule 90 is P XOR R, XOR being sum mod 2, and rule 30, for example, is P XOR Q or R. So it's a very, very, very simple Boolean expression, P XOR Q or R. It's remarkable that from an expression that simple, you get all of this behavior. But we can see these different rules. Sometimes rules that have rather complicated Boolean expressions, minimal Boolean expressions, actually have rather simple behavior, at least when you start them off from just one black cell. But anyway, that's a little bit on that. Now, rule 150, I was talking about rule 150. One can compute all kinds of things about it. In the case of sum mod 2, in the case of rule 90, one of the results is that the number of black cells on the teeth row of the pattern from rule 90 is given by 2 to the power of the number of ones in the binary decomposition of the number t. Now, in the case of rule 150, there's a similar result, but instead of just counting the number of ones in the binary decomposition of the number t, it's doing a slightly more elaborate thing, looking at runs of ones and at the lengths of runs of ones. And so, for example, I mentioned here there are total up to step 2 to the m in that pattern. The pattern kind of has a repeating form every power of 2 increase in size. There are 2 to the m times Fibonacci m plus 2th Fibonacci number. So that's, again, a sort of Fibonacci connection with rule 150. Now, another rule that shows up is in that first sort of collection is rule 225. And let's just make a picture of rule 225. Let's say, let's go ahead and make rule 225 here. Oops, that's not the 225 I'm looking for. Let's say we go ahead and make it 400 steps. So this guy is, what you see here is something which is always going off to the right there. Maybe what we could do, let me see if I can do this. Let me think how to do this. I think what I want to do here is I want to say rotate left. I want to say map indexed. Rotate left, hash, comma, hash 2. Is this going to work? That. And let's see whether this is disastrous or not. Oh, no, that's very good. Okay, so there we go. So that is now, that's rule. Now what I did was I rearranged rule 225 to make it just go on the right-hand side. And you can see there that it has this nested pattern, but the nesting doesn't grow at sort of the maximum rate. Instead, it's just growing in this kind of logarithmic way. And so in the NKS book, I think, I'm sorry, no, square root kind of way. So the pattern at the tth step is about square root of 3/2 times square root of t. So that's it's kind of interesting that I looked separately at this question of sort of what are the possible growth rates of cellular automaton rules. You're growing at maximum speed. So when you have a rule that just says, if there's a cell to my left or right that's black, make me black on the next step, then that means that you're always going to grow at maximum rate. You're always going to grow at speed 1 on each side. But in this particular case with rule 225, we don't, we'll have a slightly different setup here. Let's take a look at what it actually looks like. We'll be saying, so here, it should be the case that we get, okay, so we have, we're starting off from all black here, and then we're asking sort of from that, what happens, and if you trace through this, you'll find out that you don't have, you don't have the cases that you would need to grow at linear speed. And sort of a question of what possible speeds can you grow at? The answer, I think, is pretty much any possible speed. People have studied that a bunch. I had an interesting experience, oh gosh, it must have been, 15 years ago, a little bit more. I was giving a talk at a math department, and I was, for some reason, I had decided I would talk about sort of experimental mathematics and so on. So I started at the beginning of the talk. I said, look, we got an hour here. We're going to discover something. And so I started exploring, in particular, growth rates of cellular automata, not quite the elementary cellular automata, I think, with 3 colors maybe rather than 2. I think there were a bunch of sort of older mathematicians who were more used to the kind of theorem proof approach to mathematics, and they were deeply sort of, it seemed like a deeply alien activity to just be sort of discovering in real time. That wasn't what math seminars was supposed to be about. And about 2/3 of the way through, some of the sort of older mathematicians who were there seemed to really be getting into the spirit of it, of, well, what happens if you do this? What happens if you do that? And sure enough, we discovered some interesting things. So I gave that math department a big printout of of the particular rule that we found, which is a fractional growth rule that grows at some very, very, it's not even clear what rate it grows at, what kind of function describes its growth. But I thought that was kind of a nice concrete example of experimental mathematics in action. Anyway, rule 225 is our first example of one that has a more exotic growth rate, in this particular case, square root of t. Okay, so let's see. Let's go back to here. So these are the nested elementary cellular automata. Let's keep going, looking at other ones. Okay, so these are the three kind of really exotic elementary cellular automata. Rule 30, my original and all-time favorite. Rule 45, which is pretty good too, except that I don't like the fact it has all these stripes in the background. Other than that, it's a wonderful rule. It also has the feature that I think it grows at a 2/3 rate on one side here. And then one feature of Rule 30 and Rule 45 is that they're not symmetrical. So the rules don't treat left and right neighbors the same. You could ask, is that essential in getting complicated behavior? Well, no, it isn't. Look at Rule 73. Let's make a nice picture of Rule 73 here. Let's get rid of that. Just make a picture of Rule 73. Rule 73 has stripes in the background, and it has this rather elaborate pattern. We could probably make a picture here if we, let me see, how would we do this? I think what we would do is we would say, take this. I'm going to make a picture in which I'm making it, let's try this. 1 minus 1, 2. 1 minus 1, 2. Let's see how that works. Okay, let's see if this does what I hope it will do. So what I'm trying to do here is yeah, there we go. So what I did there was I coarse-grained that picture to make it so it's only every other cell that's being shown. And so we see here this pattern where there's a lot of complicated stuff going on. But for example, in Rule 30, the center column is still a big mystery. In Rule 73, the center column is something we understand pretty well at this point. Let's just go, let's do 2,000 steps here just to see what happens. This is now more of Rule 73. And we see the growth of this kind of region of complex behavior. It's a uniform growth rate. I forget the slope. I'm sure it says in the NKS book. Let's take a look. Well, let's look at Rule 73 here. Okay, center column of cells is repetitive, alternating between black and white. In all cases, black cells appear only in blocks that are an odd number of cells wide. The more complicated central region of the pattern grows 4 cells every 7 steps. The outer region consists of blocks that are 12 cells wide and repeat every 3 steps. Now, what's remarkable to me about descriptions like this is, you know, it has a really simple rule, and yet you're quickly diving into these elaborate things with numbers and number theory and all this kind of thing, all that from this very simple rule. Now, in this case, there's a little bit that we're able to actually understand. We can talk about, you know, it goes every 4 cells every 7 steps and so on. That's something we can kind of have a narrative description of. But when it comes to sort of the full-on complexity of Rule 73, it's something that is quite inaccessible to us. It's a kind of example of computational irreducibility. Okay, let's take a look some of these other comments here. Rule 45. Boy, these are such short comments. I mean, I spent so long studying each of these rules, and they were reduced to this is all we can say. The boundary between repetition and randomness moves on average 0.17 cells per step. I'm sure that was the result of a lot of actual computation to figure that out. Okay, back to the main section here. Okay, so those are the rules that have sort of, those are the elementary rules that have this feature of kind of simple initial condition, very complicated behavior. I then started asking the question, well, what happens if you go beyond the elementary rules? What happens if you, for example, don't have just 2 colors for each cell, but have 3 colors for each cell? Or what happens if you go beyond nearest neighbors? And I start looking at that here in order to kind of reduce the total number of possible rules that have 3 colors, and nearest neighbors will be 3 to the 3 to the 3. otherwise known as that number there. Let's find out what that is called. That would be called, oh, come now, what is going on here? Oh, there we go, 7 trillion, okay. So there are 7 trillion general rules with 3 possible colors and nearest neighbors. One thing that I did, I'd done this back in the 1984 or so, is to reduce that to what I call totalistic rules, in which the value of the next cell depends only on the total of the values treated as integers in the 3 cells before. So there are a much smaller number of those. In fact, we can, let's see, how many of those are there? There must be, for this particular case, 2187. Now, one thing that I did all the time, and it's amazing, this is sort of the story of my life, is is kind of exploring the computational universe. Just, turn that telescope out to the computational universe, see what's out there, and do that by essentially, back in those days, it was generate. The screens weren't that high resolution. So a lot of the time I was just generating printouts and printouts and printouts of these kind of arrays of thumbnails. I think the idea of arrays of thumbnails is much more common in the modern world of the web and so on. In those days, it was kind of a thing one didn't see done very much, is just to make particularly not sort of computer generated thumbnails of things. But that's what I ended up doing a lot of. And let's replicate this. So we can, these are now 3 color rules. So we can let's see, these are 3 color totalistic rules. So for example, we could go ahead and say, let's make a table of array plot, cellular automaton of, and now to make a 3 color totalistic rule, we would say N31 here. That's the Wolfram language way of describing that. Let's start it off from a single, well, black cell, except we're not going to make it black. Let's have it go, let's say 50 steps. And now let's tell it to use color rules to display this. Let's say we'll use 0 goes to black, 1 goes to red, let's say 2 goes to green. No, let's do blue. 2 goes to blue. Okay, so now we're going to look at this. Let's make a table of those ones that I had here, which were the rules from 993 to 1140. So let's say N goes from 993 to 1140. So hopefully we will get those pictures. There we go. So those are the corresponding pictures. Now we'll see here, again, very much the same as what we saw in the elementary cellular automata. The totalistic ones are always symmetric just by construction. But what we see is some that are nested patterns, some that have very simple behavior, and some that are more complicated, that do more complicated things. And there's an example. I didn't put the numbers in here, but we can start exploring these. Okay, well, that guy looks really fun. I got to see what that guy does. Okay, so let's say that one at the bottom there, that will be 2 from the end, so that's 1139. One's arithmetic. That's a lot better doing this for a while. Okay, there we go. So that's that one. All right, let's try blasting that with many more steps. Let's say 500 steps. Okay, bit boring in the end. Okay, so it has some level of kind of large scale structure here, but mostly it's still a bit Rule 30 like. It's mostly kind of got that same kind of Rule 30-esque look to it. Maybe we can do our trick as before of taking just pieces from this. Let's just see what that looks like. Wow, didn't make any difference. How can that not make any difference? Well, it looks different, but it's not that different. I wonder if we take I wonder if we do it in 4, if we cut it down by 4s. Oh, how very fascinating. Oh, it's probably 3. It's probably, because it has 3 colors, it's probably alternating through 3 colors. Let's try that. Oh, there we go. Okay, so now I managed to just get the 3rd phase on the outside, and you see this really random behavior on the inside here. Okay, so anyway, back to the book. So the real question is, what kind of behavior do you get? Okay, there's one there that I'm curious about, 1086. Okay, so here are examples. of things that happen where you can start with, just a single black cell and you get these very elaborate patterns. Now, in this particular case, this will be periodic, starting from that initial cell, it turns out, but it's periodic with a very ornate kind of pattern that it produces. And these are characteristic of what I call class 4 cellular automata. That's the pattern you'll find later in the book. I talk about 1329 rule, code 1329. I call them codes for totalistic codes to distinguish them from the rules of the pure elementary general rules. So code 1329 has, as it turns out, we'll find later in the book, has all kinds of elaborate behavior if you started off from different initial conditions. But here we're just seeing it already making this very complicated structure, which has some long period here. I vaguely remember period 48, but that might be wrong. Okay, so these are just some examples of things that happen, and yet more. And again, the main thing to realize is these look pretty much like Rule 30 and Rule 45 and so on. In other words, by going to 3 colors and having our 7 trillion possible rules, we didn't really get much more. We got many detail. In detail, we got more behavior. But we didn't get anything that looks qualitatively different from what we'd already seen before. And we see here things where these are rules where we're starting to see behavior a little bit like the Rule 110 behavior that we saw with elementary rules, where we can actually see definite structures and we can see things happening. So this is, for example, this is Rule 1635. Let's take a look at that over here. Let's go 1635. And the big mystery might be, what will it do in the end? So let's look at Rule 1635 here. Okay, there it is. That's not for very many steps. That's actually for few steps. You know what? I'm going to change this color map. I am going to change that into, I'm going to change the blue to purple and the red to yellow. Let's see what that looks like. More striking. Okay. So that was 500 steps. It still hasn't kind of figured out what it's going to do. So let's go 2,000 steps. Let's see what happens then. Okay. It's going to take a little while longer because it's computing. It's got to do 2,000 times 4,000, and it's a bit big for my it's a bit big. It's anti-aliasing on this monitor because it's got too much resolution. But there you see this thing is it still hasn't decided what it's going to do. Is it going to become all periodic, or is the structure in the middle going to eventually take over? That's kind of the long arm of computational irreducibility and ultimately undecidability, reaching out and showing us that no, you can't predict what this is going to do, even though its rule is very simple. It's just this is the what is the 1635, I think, code 1635. We don't know what it's going to do. I wonder if I talk about that in the NKS book. I do not, unless it's in the main text. It might be in the main text. Let's see. Okay, there's 1635. I'm sure I have some other pictures here. There's 2049. These are ones. These are very friendly cellular automata that I've studied quite a bit. These are just yet more examples. This is an example where you might think it was just going to make a periodic pattern, but then kaboom, it explodes into this thing that has grows at a fixed rate. Let's see. This is one that I think that's 1599, one of my favorite what's it going to do type questions. That's 1599, and you can see what it's doing here. Let's take a look at that over here. Let's look at 1599 here. And what's it going to do? Let's see. Oh my gosh, look at that. That's 2,000 steps in 1599, and it still has no idea what it's going to do when it's grown up. Let's actually make that not all there. Let's just say 2,000 steps there. So there it is, doing its thing. Chunk, 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 chunk. And I kind of have always wanted to make a movie that was based on maybe 1D, maybe 2D, maybe 3D cellular automata, where there's a whole all you're seeing is all these different behaviors, and you're kind of, maybe there's some music in the background or something, and you're kind of wondering, what's it going to do? And it's kind of like it's an adventure story. What's going to happen? Is this thing going to take over? Is it going to die out? We're rooting for this particular thing here. We're rooting for that thing there. It kind of is kind of an object lesson in the notion of free will, because it's kind of something where you're imagining this thing. It has, is it going to die out? Is it going to take over? What's it going to do? But actually, in the end, it's just some simple rule that's determining it all, kind of probably a bit like how the universe works. Okay, let's go to 3,000 steps here. Let's see whether it can figure out what it's going to do. So here it goes, it's growing. Is it going to, what's going to happen? Is it going to take over? What's going to happen? What's going to happen? What's going to happen? What's going to happen? Oh, it hasn't decided yet. Oh boy, we have to go even further. Let's go, how long do we have to go? Let's go, all right, let's really go big. Let's go 6,000 steps here. Again, I'm giving you, okay, so let's scroll down. What's it gonna do? Okay, it seems to be taking over. It seems just to be getting kind of random here. What's gonna happen? What's gonna happen? What's gonna happen? What is going to happen? I do not know what's gonna happen. Okay, things are filling in again. It's oh my gosh. Oh my gosh. Okay, let's one more time here. Let's go to 10,000 steps. Let's see whether we can figure out what's going to happen after 10,000 steps. So this is kind of, undecidability, computational irreducibility in action. We really don't know what this is going to do. We run it for some large number of steps. Let's see whether we can imagine, can we make some sort of mathematical style prediction, given that we're looking like this? What's it going to do? What's going to take over? Let's keep going. Let's keep going. Let's keep going. It doesn't seem to be growing anymore. So that's kind of a sign. Maybe it's not going to make it. Maybe it's not going to make it. What's going to happen here? I feel like a commentator for some sport. Oh, there we go. It's over. It dies out. And but at least for this particular initial condition, it dies out. Were we to change the initial condition, it'd be a whole different question that we'd have to ask. I think in the NKS book, it says the outcome of evolution finally becomes clear after 8,282 steps, when the pattern resolves into 31 simple repetitive structures. All that from code 1599. Okay, so we're kind of learning in cellular automata, very complicated behavior from very simple initial conditions. So then the question that I had back in 1991 was, okay, that's what happens with cellular automata. What's important about cellular automata that makes these phenomena occur? Is it important, for example, that a cellular automaton operates in parallel, that all these cells are updated in parallel? Or would you be able to see similar phenomena even if you just updated one cell at a time? So questions like that are what launched the rest of chapter 3, which was looking at kind of what can we change from the way cellular automata are set up, and what happens when we make those changes, what happens to other kinds of systems in the computational universe. So the next thing I looked at was mobile automata. So these are things I kind of came up with as sort of a minimal kind of way of just doing one thing at a time. In a cellular automaton, every cell updated according to the same rule at the same time. In a mobile automaton, the way it works is you have an active cell, a head, so to speak, and all you do is you only look at the place where there's that active cell, and then you have rules that are like the cellular automaton rules, but those rules only operate at the position of that active cell. And the rules specify not only what the color of the new cell in the center will be, but also whether the active cell will move to the left or the right. So this is an example of a mobile automaton starting off from a blank initial tape, completely blank. It can do that. An ordinary cellular automaton, if you started off with a completely blank initial condition, it can never develop any structure. But here you've got sort of a distinguished cell that's associated with where the active site is in the mobile automaton. And in this particular case, the mobile automaton wiggles backwards and forwards, producing this kind of pattern. I'm sure I show what happens after a little bit longer. I think that's one of the ones over here. What you see is the thing is kind of going backwards and forwards. Each time it's going a little bit further than it did before, probably going out square root of time, a square root size distance. So the mobile automata, again, we're now looking only one active cell. By the way, mobile automata will reoccur later on in the book in chapter 9, where I talk about fundamental physics, because they were my kind of minimal model for sort of how an observer interacts with the universe. And they're what led me to things, causal graphs, and what eventually led me to things like causal invariance, and a lot of the foundations of what's now our physics project. So mobile automata had a big effect there. I would say mobile automata are something that have not been studied as much as they should have been. They're still kind of very much out there to be studied. I would say about cellular automata as well. Here's the crazy thing. I found some new things about simple one-dimensional cellular automata just a couple of days ago. So it's kind of like there's this infinite ocean of things to discover, even within that those very simply defined rules. Even the elementary cellular automata, people, including myself, make new discoveries about them with some regularity. There's a huge amount still to discover. With Rule 30, I mentioned last time, I've got these Rule 30 prizes out there to answer questions about Rule 30. It's an infinite story, and that's what computational irreducibility does for one. But anyway, mobile automata, even less is known about mobile automata than about cellular automata. But okay, how can you compare mobile automata and cellular automata? Well, one obvious thing to do is to say, let me make a compressed evolution for a mobile automaton, where instead of looking at all the different steps here, I only look at those steps where the head has gone further to the left or right than it's ever been before. So we're doing this kind of compression, and then we're getting something which looks a lot more like a cellular automaton pattern here. It's almost as if, were we to update a cellular automaton on a sequential computer, we are ultimately going through and updating, this position, that position, that position. But in a cellular automaton, we're doing all those positions in parallel. So in terms of implementation, you're kind of keeping a copy of the previous state, and you're going through and you're doing the updates based on where every update is based on the previous state to get the new state. Whereas in a mobile automaton, you're not doing that. You're just updating in this one position, and you're leaving everything else the same. So, okay, so now what's going to happen here? Well, we can look at mobile automata, and we can start looking at what kinds of behavior you can get. This is a more elaborate mobile automaton. This particular case, it's a little bit generalized, because instead of filling in the value just of the center cell, it fills in the values of the two neighboring cells as well. So it's kind of block-to-block transformation. So the question is, what's going to happen here? And again, rather simple behavior. But if you keep going, ta-da, one of those rules produces behavior that is just like a cellular automaton. When you look at its compressed behavior, and you see that the whole sort of story of it going backwards and forwards and where its head goes, that's again a complicated thing. Now, I'm sure I've got, let's take a look. I've probably got some examples of, this is asking, how often do mobile automata have different kinds of behavior? And I wonder if I'm sure I've got something here. Maybe not. Okay. Let's see. Here we go. This is a case where even the head motion, look at that head motion there, or the active cell motion, even the head motion is really random looking. And the behavior you get is correspondingly random. Let's see if I have a picture here. Okay, so there are some sort of traces of sort of random walk-like traces that you get from mobile automata. Again, hasn't been studied very much, a good thing to study. There are cases in which you get fairly simple behavior, but I'm sure that's a digit counting, binary digit counting case, but then you get this very complicated behavior. So mobile automata, first example where we're not looking, where things aren't all being updated in parallel, but doesn't matter. We still get the same phenomenon of simple rules, very complicated final behavior. Although it's a little harder to find than in cellular automata. These systems are a little bit less active, and so it takes a little bit, you have to look through more rules to get to ones where you start seeing very complicated behavior, as opposed to them being sort of obviously simple in their behavior. Okay, so next up, I think this was, what is this? Oh yeah, this is something hardly studied at all. These are generalized mobile automata in which you can have multiple heads running around. And in a sense, these really should be studied as multi-way systems, kinds of things that we've really studied intensely in the physics project, although they were introduced in NKS. A multi-way system where you can kind of pick different ways that the head could go, but this is one where you have sort of lots of heads, so to speak. So this is something where you can see in these pictures that it's full of heads. They're dots all over the place. And that's a case where you are updating only when there is an active cell, but there can be many active cells on a given step. Again, these generalized mobile automata hardly studied at all. Something out in the computational universe, just waiting for somebody to really study them. And this whole field of studying simple programs, we're now calling it ruleology. This is a new name for it. And we're intending to have a whole ruleological society and so on, and a whole collection of activities around this thing, which I view as being a very fundamental area of science, of exploring the computational universe. There is much ruleology to be done about mobile automata and generalized mobile automata. It's wide open, so to speak. All right, onward we go. So Turing machines. Turing machines are pretty like mobile automata. Mobile automata are a little bit simpler than Turing machines. Alan Turing could have come up with mobile automata, but he was the actual Turing machine that Alan Turing first came up with is something vastly more complicated, although the same in structure as what I'm talking about here. Here's the typical setup of a Turing machine. You have just a single active site, and it has but instead of the mobile automaton, where you're looking at neighboring values to decide what to do, here you look at the color of that cell under the head, and you look at the state of the head. So in this particular case, the head has three possible states indicated by the three orientations of that cell there. And this is, and then you can ask, well, what does this do? And it's very much like mobile automaton. Let me see if I can show you that particular one, because we have all of this stuff in Morphem language. Wait a minute. Come on now, numbering scheme. Okay, 3024, let's try that one. Okay, so let's say we go over here and we say rule plot Turing machine 3024. See what that looks like. Okay, that's a, I bet that's showing a two-state Turing machine. I bet that the actual case here is a three-state Turing machine. I bet we do that with a 3,2 there. There we go. Okay, so those are the rules for our Turing machine. And now if we want to find out what it will do, we can go ahead and say here, let me see, what do we want to do? We want to say Turing machine, and we want to start it off from the initial condition. I think we want a blank. What do we want to do? We want to say state one and otherwise blank, I think. Let's try that. Initial tape must be this. Okay, well, this is a read the documentation moment. Okay, Turing machine isn't quite as, here we go. So let's look at this. Let's pick that out of documentation. Okay, so here now we will have, that's a very simple Turing machine, and that's it. That's a two-state Turing machine. Its head can be either up or down, and this is what it does. So let's run it for, let's say, 200 steps, and we see that all it does is wiggle backwards and forwards like that. So with Turing machines, again, we have the question, are they going to do something complicated? How far do we have to go? Or are Turing machines going to be somehow something, when Alan Turing first invented Turing machines, he looked at, in 1936, he looked at a very complicated Turing machine. I wonder whether I say how big his Turing machine was. No, I don't think I do. But his Turing machine was absolutely huge. And he was really mostly interested in sort of the theoretical question of whether a Turing machine could be made that would emulate other Turing machines just by being given different initial conditions. That was kind of the concept of computational universality that was clarified with Turing machines. Okay, let's look at the two-state, two-color Turing machines. There are 4,096 of those. I could probably just make a picture here. Let's just go ahead and do that. let's do them only for like 30 steps or something. And let's say, let's just do n there. Let's make, I think these are mostly going to be super boring. Let's go, let's say n, I don't know whether we want to go all 4096, but let's go, let's go 1,000. Let's go just 200 to begin with. Yeah, I think it's taking it longer than it might have done because there's a lot of fiddly things to be filled in. Oh my gosh, those are boring Turing machines. Look at that. Okay, we're finally getting something to happen here. Boring. Okay, let's go and look at the Turing machines in a slightly larger. Let's say between 2,000 and 2,200, for example. Oops. So those are Turing machines. Again, you can number Turing machines just like you can number elementary cellular automata. It's a little bit fiddlier than elementary cellular automata. Okay, now we've got some Turing machines that actually do something. Okay, so this Turing machine, it wiggles backwards and forwards, and you can see I didn't put grid squares on here, but you can see it's kind of growing its pattern, and it knows when to grow based on the states of its head. Let's see whether any of these do anything more interesting. Pretty boring there, but if you go on. And in the NKS book, I talk about sort of all of the different rules. Okay, this one here, rule F. Which one is rule F? Numbering of Turing machine rules, rule F. Oh, numbering. Let's see. I must say what it is. 1953. Okay, a little bit before my time, but let's see. 1953 here. Let's go ahead and look at rule 1953. And see whether we can figure out what it does. Again, it's a big exercise in Turing machines. There's one Turing machine I talk about in the book. Okay, there's 1953. What is it doing? Who can figure out what it's doing here? Let's go ahead and add a mesh here. There's rule 1953. What is it doing? Let's go extend it a bit longer. Let's go for, let's say, 100 steps here. Oh, I shouldn't have put the mesh in there. Okay, a little hard to see here, but I'll tell you the answer. This is a binary counter. Eventually, this will count up in binary. It's a little bit confused in the way it's arranging things, but essentially there's the number 1000, there's 11111. So this is growing logarithmically in size, and it is this Turing machine, that particular Turing machine, so we can look at what rule it has. This particular Turing machine, in a sense, is a useful Turing machine in the sense that it is a binary counter. Sort of fishing out of this universe of Turing machines, here's one that we can sort of say, we can explain what it's doing. Okay, so that was that's sort of the binary counter is kind of the most complicated things that happen with two-color, two-cell, two-state, two-color Turing machines. And actually, my friend Marvin Minsky had looked at two-state, two-color Turing machines back in the 1960s, early 1960s, and discovered none of them did anything interesting. And so from that, he concluded basically, there can't be anything interesting that happens in very simple Turing machines. Well, turns out it's not true. If you go to three-state Turing machines or to two-state, three-color, but this is now three-state Turing machines, here's some of what they do. Much more complicated behavior. Immediately, you see more complicated behavior. Here's an example. I think this is a four-state Turing machine, like that mobile automaton that we saw earlier. Even this is where we're seeing successive stripes of evolution here. Even the motion of the head is extremely complicated. And that's the compressed evolution down there. I think I might have, let me see. No, maybe not. Turing machine 596440. That's, I think, this Turing machine. Yes. And oh my gosh, these things get so complicated. This thing has a nested pattern in some part of the region. In the compressed evolution, some part of it is nested with some quite complicated function. The first T steps of compressed evolution are given by this complicated piece of code here, recursive code. Then it says the glitches on the right-hand side have this pattern. So if you were to observe those in some physical experiment somewhere, you would just say, perhaps there must be some very complicated cause to this elaborate pattern of glitches. But no, actually, Turing machine 596440 would be perfectly adequate to produce that behavior. So in Turing machines, sort of the big discovery here is it doesn't matter that the Turing machines are that there's just a that you're just dealing with a single cell, single head. The same thing that happens in let's see. Oh yeah, here we go. The same thing that happens in cellular automata happens in Turing machines. Even very simple ones can produce extremely complicated behavior. And later on, later in the book, I kind of wondered about this 2-3 Turing machine, two-state, 3-color Turing machine. This was the simplest one that produced very complicated behavior just from a blank tape. And it turns out that, sure enough, this one was proved in 2007 to be computation universal. So in a sense, even though it's sort of one of the very simplest possible Turing machines, it's the simplest one that doesn't show obviously simple behavior, it turns out to be computation universal. And that's a big piece of evidence for my principle of computational equivalence. But sort of the discovery, the empirical discovery that complicated behavior could occur even in simple Turing machines was what kind of provided the conceptual fodder, the empirical data necessary to formulate the principle of computational equivalence. So that's Turing machines. Let's go on. So next in my collection in chapter 3 are substitution systems. So substitution systems have a completely different idea. In a Turing machine or in a cellular automaton, they're a fixed arrangement of cells. So there's a fixed structure of space. In substitution systems, instead, one just has a sequence of cells and one's continually rewriting that sequence, perhaps changing the number of cells. And by the way, string substitution systems, which is essentially what these are an important sort of piece of intuition building necessary for the physics project. There's something we're using extensively in the physics project. In fact, the things I've been doing recently in metamathematics make use of things like this again as kind of minimal models for what's going on. So they kind of appear here in chapter 3 of NKS. These are sort of examples of what happens. So this is one where black cell goes to black, white goes to white, black, and things grow exponentially here in this particular, and then here's one, black goes to white goes to white, black. Again, it grows exponentially. This grows like by a factor of 2 every step because every one cell goes to 2 at every step. Here, you get both one cell going to one cell and one cell going to 2 cells. This is a Fibonacci sequence, and it grows with Fibonacci numbers. So there are different ways. It's kind of a nuisance to represent these things because the number of cells is growing rapidly. So you're kind of getting something where every cell, but you can think about it as every cell, if you just are looking at cases where, for example, every cell subdivides into, well, every cell is subdividing, you can think of it as a subdivision process. So here is that this is one case here where the subdivision eventually leads you always to periodic structures. In this case, the subdivision leads you to a structure which is never periodic. In this case, this is the Fibonacci case. Again, it leads you to a structure that's never periodic. Here's one where it's kind of constantly subdividing space. This corresponds to the Cantor set that was discussed beginning of the end of the 1800s. In slightly different contexts as a way of kind of drilling down into the real numbers and selecting just parts of the real numbers. Well, there are different ways to visualize substitution systems. Here are a bunch of other substitution systems, and here's substitution systems represented as trees. So instead of looking at subdivision of a complete interval, we're instead saying this is the first step. This is the first thing is a single element that bifurcates into 2 and so on. That makes an ordinary binary tree. The coloring at the end is either very simple and periodic, or it might have this more elaborate pattern. There's a Fibonacci tree, and so on. So there's an endless amount that substitution systems, unlike many of the other systems in the NKS book and in the computational universe, these substitution systems are amenable to extensive mathematical analysis. And over the course of multiple hundreds of years, many things have been done about what amount to these neighbor-independent substitution systems. Why do I call them neighbor-independent? The reason is that I'm saying every time you have one of the cells here, or it just, depending on whether it's black or white, that determines how it subdivides. You don't need to know anything about its neighbors. You just need to know what the color of that cell is, and it will determine how it will subdivide. So in this tree, anytime there's a black branch, it always divides into black-white. Every time a white branch, white-black, and that happens context independently wherever those branches occur. So we can do all kinds of things. We can make an easy mathematical analysis of the growth rate. It's just given by powers of matrices. It's like Markov chains, and that's an easy thing to do. We can, well, this is, I'm talking about Fibonacci numbers here, where, there were actually all kinds of strange things in the notes to the NKS book. There's much to be found, like mod of Fibonacci of n, comma n is something where it appears to be 0 only when n is of the form 5 to the m or 12q, where q is not prime. That was finally proved by a chap called Eric Rowland, who came to our first summer school. I think he explored this at length, but it's that was just something that I found as a piece of experimental mathematics, and many among 1,000 other things hidden in the notes to the NKS book are all those random kinds of discoveries. But that particular one was about Fibonacci numbers. Okay, so there's a very close connection between substitution systems and digit sequences. Essentially, what's happening is that what you're doing is, as you do that subdivision, you're kind of exploring. Well, you can think about it in terms of a binary tree. The binary tree, every branch of the binary tree can be labeled by a different digit sequence. And when you have that kind of substitution system that is telling you what color each thing will be based on those branches, then you end up getting that will give you that gives you, well, you can see the correspondence between digit sequences. Basically, the nth term in the sequence generated by the substitution system will be determined by the binary number that corresponds to n. So in particular, let me see here. Where are they? Maybe here. Okay, so this is the Turing-Morse sequence. Is a very famous sequence that is the one that you get by just going 1 goes to 1, 0, 0 goes to 0, 1, and the color of the nth cell is given by the digit count function, by whether they're an odd or even number of ones in the binary decomposition of n. So that's and this sequence just has many different ways of characterizing it. Here it is in terms of, this is kind of an elaborate thing. This is it with a generating function. It just has a lot of different properties, and it shows up in lots of different places. And it has all sorts of features, like runs of 3 identical elements never occur. There are all sorts of properties. It's a very nice kind of sequence. It's been you could actually make kind of metamaterials, quasi materials where you have layers that are Turing-Morse sequences of layers, and they have all kinds of wild properties. It's kind of like not quite a crystal. It's kind of a quasi-crystal kind of thing. It is a nested pattern, but it is not a periodic pattern. Similarly, there's lots to be said about the Fibonacci case. In general, lots to be said about these different kinds of sequences, the different sequences made by neighbor-independent substitution systems. There's a connection with square roots. This is something where when you have a line at a square root angle and you imagine kind of drawing that on a raster display, which just has a fixed grid of cells, the question of where you actually draw black cells is determined by one of these substitution systems. There's also a relationship to paper folding and dragon sequences and so on. You can think about these substitution systems as corresponding to paper folding processes. They have a rich history, as I mentioned here. Axel Tui, kind of a logician, 1906, talking about the Turing-Morse sequence. Aristid Lindenmayer, who was a biologist primarily. I met him once, very nice old chap when I met him. Invented these things that got called L systems, which were kind of branching systems. Subsequently, Alvy Ray Smith, another person I've known for many years, took that idea of L systems and started actually using them to make artificial plants. He was a founder of Pixar, and there were many artificial plants produced using L systems. The kind of thing that I've talked about, these neighbor-independent systems, are so-called 0L systems. The zero means that there's no dependence on any neighbors. I talk about here the I Ching is sort of an example of something which you can think of. The hexagrams of the I Ching correspond to sort of levels in these substitution systems and so on. So there's lots of different things here. Many people, let's see, this is the C curve. I think this must be, oh no, I don't discuss, I discuss that later on in the book. I discuss the relationship of this to kind of the two-dimensional case. All right, I'm just keeping on going here. I'll show you, this is, if we don't assume neighbor independence, if we allow cells to, like in biology, for example, we allow cells to bifurcate sometimes, depending on their neighborhood, then we can get more elaborate patterns. We no longer have these purely nested patterns. These are neighbor-dependent substitution systems. Again, these have not been studied very much. They really should be studied more. They are pretty good minimal models for various kinds of biological processes, I think. And once again, just like, so in the case of neighbor-independent substitution systems, all you can ever get is nested patterns. They are sort of the one example in chapter 3 of a system that does not have the capability to sort of go full Rule 30, Rule 110, kind of go out and sort of engage with the principle of computational equivalence. But as soon as you have any neighbor dependence, all bets are off, and you can have very complicated behavior. Here are some examples of neighbor-dependent substitution systems. Again, kind of like showing, it's kind of a bit like a cellular automaton, except that the total number of cells can expand or contract. And that's what you see in these cases here. So neighbor-dependent substitution systems, same kind of behavior. Okay, let's consider another case, sequential substitution systems. These were a little bit black sheep systems until recently, because recently they end up being very critical to our development of multi-computation and things we've done in the physics project. What's the idea of a sequential substitution system? In an ordinary substitution system, at every step, you're doing all updates in parallel. So in a neighbor-independent substitution system, that's a very straightforward thing to do. Just take every cell and rewrite it according to what you wanted to rewrite it as, or what the rules said. But in a neighbor dependence, it's a little bit more tricky because you have to do something like a cellular automaton, where you say, I'm going to take the existing cells, I'm going to look at what they are, and then I'm going to rewrite a new version of them. In a sequential substitution system, it's much more like a mobile automaton. There are a particular place where you actually do the rewrite. And so one rule you can use for a sequential substitution system is just you start at the beginning of the string and you keep scanning, kind of like a text editor. You say, I'm going to do a find and replace, and I'm just going to do it in the first place. I'm going to do the replacement, the first place I find that my pattern applies. It's actually similar to the way that the pattern matcher in Wolfram language works. It sort of does the first update it can find that applies. So this is a do something only in one place kind of story. So here's a sequential substitution system where it says if you ever see white, black, white, or you just see white, then you make these replacements, and this is what it does. And you see it kind of growing a bigger and bigger pattern here. Keep going, and needless to say, just like all these other systems, it doesn't take a very complicated rule. And then suddenly, and just purely in this kind of iterated text editor, you're getting behavior like this, very elaborate behavior. So sequential substitution systems have this feature, just like all these other things we've talked about. There's a compressed sequential substitution system where we're only showing it when the size of the array got bigger than it ever had been before. This is, again, that's the rule down there. This is the behavior, very complicated behavior again. This is that case. Now, a sequential substitution system, might say, there's some, I talk about text editors like Tico and Snowball and so on here in connection with sort of places where this has occurred. Now, sequential substitution systems get much more exciting when you ask the question, well, what actual sequential order should I use? What traversal order, what updating order should I use? I've sort of been wondering about that question for like more than 40 years, because it's a central one in thinking about sort of the evaluation process in something like Wolfram language. Finally, with the physics project and these ideas about multi-computation, we're actually going to solve that problem. But the sequential substitution systems are kind of the minimal example where you're always just doing a left to right scan and doing one update. Another thing you might do is do a left to right scan and do as many updates as you can. That would be so-called generational updating in our physics project. Again, it's very interesting to me to see how all these things, I explored what seemed like the obvious kinds of simplest possible computational systems in chapter 3, and every one of these things has come back. And essentially every one of them has now come back and has turned out to be an important kind of foundation for a piece of the foundations for what's now turned into things like the physics project. So that's sequential substitution systems. Let's keep going. All right, so a sequential substitution system, again, you're only doing one thing at a time. Even so, you get very complicated behavior. Let's think about other things. Let's imagine that you don't even allow yourself to do the update everywhere in the string. Let's say you only allow the update at the very end of the string. That leads us to things called tag systems. And a tag system, you basically are looking at the front of the string, and depending on, you're chopping off the front, and depending on what was there in the front, you add stuff in the back. How could that do anything complicated? Well, in these simplest examples, it doesn't. But turns out you don't have to go very far before you start getting cases where, for example, the length of the string you get is very hard to predict. And in fact, with tag systems, you might have thought, oh, that will be another thing that I won't have sort of encountered again. But you would be wrong, because in fact, if we look at tag systems were invented just around 100 years ago, last year, and by a person called Emil Post. This is, in fact, this is the particular tag system he looked at in that picture there. And it's just chops off one thing at the front and it adds either 2 things or 4 things at the back. And this is kind of its behavior. And I did this whole giant study of tag systems, and boy, are they complicated. In fact, just the very specific tag system that Emil Post tried to study, he kind of realized that if he could solve tag systems in general, he could sort of solve all of mathematics. All he needed to do was to solve tag systems, but that turned out to be, in a sense, irreducibly hard. And this is now, so that one little section of a few pages in the NKS book turned into this giant treatise on tag systems here. These are the actual behaviors of that very specific tag system that Emil Post had looked at. There are other tag systems I discuss here, which are ones that are the ones that I specifically looked at in the NKS book and so on. I think I even discuss, I went a lot further here looking at the ones that were in the NKS book. So again, that one section turned into a big discussion here. It's connected to the 3n+1 problem that is a kind of an unsolved number theory problem. It's connected to the Riemann hypothesis. It's a whole elaborate story, but that's kind of where tag systems went. Even simpler than tag systems are what I called cyclic tag systems. In a tag system, the question of what you get, what you add to the end of you can add different things depending on what the initial values of cells were, and you can have multiple initial cells that you cut off and so on. In a cyclic tag system, all you're doing is you're cyclically going, you go one state, another state, one state, another state, and at each step, you're either deciding to add something or not. If there's a black cell at the beginning, you at the even numbered step in this particular case, in the even numbered steps, you add 1, 1. In the odd numbered steps, you add 1, 0. So there's kind of the only thing you need to know is, are you going to add or not going to add? And it's if there's a black cell in front, you add, and if there's a not, you don't. So that's all you need. And once again, I'm kind of spoiling it here, but once again, even with a cyclic tag system where all you're specifying is just something like 1, 1, 1, 0. Or in this case, let's see, 1 or 1, 0, 1, just 1 and 1, 0, 1. That's the pattern of lengths of strings that you get with a cyclic tag system. So again, very, very minimal kind of kind of thing. These reappeared in reappeared in studying Rule 110 and proving universality of the Rule 110 cellular automaton. Cyclic tag systems, well, there's kind of a chain. It's kind of like when you want to translate from some very obscure human language to English, you might be going through a chain of 4 other languages to get there, so to speak. So similarly, in showing that Rule 110 cellular automaton is computation universal, kind of go through cyclic tag systems to a kind of generalized tag system, to a Turing machine, and that from there to universality, so to speak. So cyclic tag systems are sort of a minimal case. Now, cyclic tag systems have the feature that it's kind of fun because you can actually make a mechanical implementation, and this has been done recently, a mechanical implementation of a cyclic tag system. It's such a simple system. You can do something with just a sequence of balls, and you can, it's kind of a great museum exhibit. I don't think anybody's actually built it as a museum exhibit yet, where you literally have a mechanical device that is generating randomness through a very simple process. So that's kind of the story of cyclic tag systems. Okay, keeping on going. The next thing we're almost there actually here. I'm probably going to be another just a minute. Okay, all of these things that we've discussed so far are all like bit patterns and arrays and so on. There's another minimal model of computation. I'm going to talk about 2 more minimal models of computation. Another minimal model of computation is register machines. Register machines are kind of like a minimal representation of the machine code of a computer. They're set up, they have a program, and the program has only 2 kinds of instructions. Increment a register contains an integer, or decrement a register, and if the register is 0, jump to another part of the program. So this is a very simple program here, written in something like a machine code, where you say this is an increment instruction, and then you do the increment instruction, and you go on to the next instruction. The next instruction here is a decrement instruction, and that decrement instruction jumps back to the first instruction if it's 0. So we see here, this is the program counter, and it's moving from this program element to that program element. It goes, the first program element, okay, it increments the register here, and then it gets to that second position there. At that second position, it then decrements the register, but because it reached 0, that means it jumps back to that first position, so the thing keeps on wiggling backwards and forwards. Okay, so here's a case where we've got 2 registers, and this is now the program counter just keeps on going, scanning through the possible instructions in the program, and you see that it's making the first register just progressively go up, although it sometimes goes down a bit, and the second register will progressively go up every 4 steps. Okay, so we've got an increment and a decrement jump instruction, and that's our kind of machine code. And so now we can look at, well, what can happen in register machines. So this is a 2-register register machine. This is one which has 5 instructions, and you see this is its flow. It's kind of if statement flow. It's go-tos and so on. It's very, very sort of low-level machine code-like thing. And you see here, this is the behavior you get. That's the behavior of the program counter. That's the values of the registers. Okay, so the question is, there are 250,000 register machines like this. This is the most complicated behavior you get. Then, of course, I kept on looking, and I think it took me like maybe a few weeks of CPU time to do this on many computers back in the early 1990s. Probably be a lot faster today. The 11 trillionth register machine, ta-da! There's this creature here. 2 registers, 8 instructions. That pattern of flow, there's the behavior. Now, it looks like it's pretty regular. It looks like it's just increasing, decreasing, increasing, decreasing. But if you summarize it by looking at just the values of the registers when they're bigger than they've ever been before, this is what you get. If you then take the numbers you get out, this is what you get. So in fact, this register machine is the simplest register machine that produces complicated behavior, and that complicated behavior is something that actually is very close to the 3n plus 1 problem. This particular thing, the next value is 3n over 2 if n is even, and 3n plus 1 over 2 if n is odd. And that is also related to the digits of powers of 3 in base 2, but it's an example of something where you are getting the same kind of complicated behavior. I'll talk next time about systems based on numbers, where we'll talk a bit more about digits of base powers of 3 in base 2. But in the register machines, even though it's a totally different kind of system from something like a cellular automata and a Turing machine, whatever else, same story happens again. Very simple rule, still gets very complicated behavior, even kind of a naturally occurring rule. So it took a little bit longer to find something that wasn't really kind of dumb and simple in the register machines, but again, we were successful in doing it. So another sort of piece of evidence for the principle of computational equivalence. Oh, I love the fact that I knew that when I was writing this, that there were certain kinds of things in the NKS book that would be, I talk about, well, in actual low-level languages like C, BASIC, Java, or Assembler. I guess that's still valid, although BASIC might be a little bit going out of circulation by now. Although it shouldn't, it's a good language. It was a language of, anyway, I talk a little bit about random programs and the idea of actually looking at random assembly language. And I actually tried some experiments back in the day on that. I suppose it would be easier with LLVM and some of our compiler tooling and so on to do that, to look at genuinely random programs, actual programs for a computer. Okay, so register machines, as I say, sort of an idealization for the arithmetic logic unit of a real computer. Again, same kind of thing as with cellular automata. Simple rules, complicated behavior. Okay, the final type of system that I looked at in chapter 3 is what I called symbolic systems. Again, this was just a few pages in chapter 3, and it's turned into, well, I wrote a couple of hundred pages about these last year, and I just wrote a couple of hundred pages in the last few weeks, well, in the last few months, but it's getting finished in the last few weeks about them. So they are, even though it was just a few pages here, they turned into something much bigger. And actually, they had a long history because symbolic systems are kind of a minimal version of Wolfram language, a minimal version of combinators. And so what they are is something where you're doing pattern matching. You say E of X blank, Y blank goes to X of X of Y, for example. So with that rule, we're saying this expression, E of E, whatever, we can think of that expression as being like a tree structured expression. And then we are going, we're applying those rules, and we're applying them to all the different subparts of that tree to rewrite them and generating these outputs. And it's a little bit more abstract to understand what's going on, because we're essentially transforming trees according to these pattern matching rules. So here's an extremely minimal case. This is, oh no, sorry, that's still the rule from the previous page of X of Y type rule, starting off from different initial conditions. And one question you can ask is, will it ever halt? So you can see in this case, it goes to a lot of trouble. It starts from that initial condition, goes to a lot of trouble here, and eventually it halts. You say, how long does it take to halt? Well, turns out that the maximum time to halt from a thing of length n cell length is 2 to the 2 to the 2 to the 2 to the 2, where the power tower is iterated n times. So it's the tetration of it's the nested power n times nested. So this thing, it does eventually halt, but it takes that outrageously long time to halt with this particular rule. Now, in general, let's see, I think I talk about that here. You can actually understand that in terms of things called Church numerals, named after Alonzo Church, where he studied these things in lambda calculus. You can understand why there's that kind of fixed point of it always going to halting. Let's see. Well, there's a lot of discussion here about different kinds of things. But once again, you can ask the question, well, this particular one, that first one we looked at there, it always halts, although it does in a rather elaborate, if nested kind of way. The question is, what happens with the rules? And just for once, again, in the even though the rule is very simple, the behavior can be very complicated. And these are sort of the growth rates of these kinds of things. Now, I will say that one of the things that I did in studying symbolic systems here was there's a big question about what order you do these rewrites in. And I will say that the very simplest symbolic systems not the very simplest. The first ones to really be looked at were in 1920 by Moses Schoenfinkel, were combinators, which are this pair of symbolic systems. S of x, y, z goes to x of z, y of z, k of x, y goes to x. And one of the big issues is, well, you do these different kinds of rewritings, but what order do you do the rewriting in? And that is a very complicated question. And that leads us into multi-way systems and so on. I should say that even with just those combinators, I looked at the end of 2020, in the 100th anniversary of combinators, I decided to go actually explore what can we do now 100 years later with combinators. And oh my gosh, it's so complicated. Here are simple combinator expressions, essentially initial conditions for symbolic systems, and they do really, really complicated things. Here's one that has a kind of nested behavior. I think there's one here that kind of wiggles back and forth and does all those very, very complicated things. Eventually, I think after 36 million steps, it eventually dies out. So again, extremely complicated behavior. And by the way, in the case of just those combinators, they can sometimes die out, sometimes grow forever. The behavior is very complicated. So that thing, which was just a couple of pages in the NKS book, turned into this giant tome. There's a book version of this that came out last year. There's my book about combinators. You can view that as being just a little piece of one section. One section of chapter 3 turns into another book. The big question is sort of in what order do you do the updates? That leads to multi-way systems. That leads to lots of other things about studying what happens in quantum mechanics and physics, and now in what I might call the quantum metamathematics that I've been studying recently. That's all things that come out of sort of this the study of these symbolic systems at the end of chapter 3 of the NKS book. And I will say that with symbolic systems, again, it's like we're only in the very, very, very early stages of studying these things. Even at this point, it's a sort of vastly wide open kind of releological area. Well, so in the NKS book, I talk about at the end of chapter 3, I pretty much am summarizing what we've seen here. And the big summary is it doesn't really matter. After you get beyond the obviously simple behavior of these systems, you get into this zone of sort of maximal complexity. And that's kind of what led me to this principle of computational equivalence. Here's an example based on cellular automata, looking at ones with 2 colors, 3 colors, 4 colors, 5 colors. And you can't really tell that these are 5 color as opposed to 3 color. You've kind of maxed out in complexity already in the 3 color case. And that's kind of the big story of the principle of computational equivalence. Once you are above this very low threshold, you are in systems which have kind of are equivalent in their computational sophistication, are of maximal computational sophistication. Now, I think at the end of chapter 3, I also have a discussion of kind of how the discoveries in this chapter were made. This is mostly about the methodology of computer experimentation and the methodology of using Wolfram language to do these kinds of things. I talk a bit about the history of experimental mathematics and the history of, of kind of the idea of studying simple systems, kind of a little bit about what the kind of the aesthetics and the care that you need to take in exploring these simple systems. I think that one of the things that I kind of my mantra in doing these kinds of investigations is whenever you study these things, you're always saying, well, I wonder if this system can do this. And often you have the theory, this system is too simple to ever do that. Those theories are usually wrong. I mean, my usual way of saying it these days is the computational animals are always smarter than we are. Even if you think you can see that this kind of system can never do anything complicated, it will prove you wrong. Now, when I was doing these experiments back in 1991, 1992, one of the things that was always a big issue was I would try and do these big automated things to study, can I find a register machine that has particular behavior or whatever else? And one of the challenges was don't assume things when you make your net to catch things. Because, for example, I don't remember all the details. I could look it up. I think in register machines, I was pretty sure nothing happened, but then I had to be more careful, and I realized, well, actually, something complicated happens. My net was just too coarse to catch those little creatures that were showing exactly what I wanted to see. So in other words, it's a question of doing careful experiments, just like when one does physical experiments. One has to do them with care. One has to also not assume that one knows the answer, but one has to kind of, so many times I've like, this is finally a kind of system where it's not going to do anything complicated. Oh, actually it does. And of course, when you've seen that happen a dozen times, you start realizing there's got to be a bigger principle about this. And that's where the principle of computational equivalence came from. Okay, so that's what I was going to say about chapter 3. Now, I'm happy if people have questions or comments. I'm happy to try and address some of those. Oh, lots of questions here. All right, let me take a look. Okay. There's a question here about what does it mean to have a speed of half a cell per step? What it means is that every 2 steps you move out 1 cell. And so, for example, that can happen. Let's say you have a 3-color cellular automaton, and it's going, red, I don't know, black, red, blue. Then when you have a red cell on the outside, it can, for example, turn into a blue cell, but not go further out. And then the blue cell can be one that will actually go further out and produce a red cell there. So in other words, it's alternating. The edge of the pattern is alternating between red and blue, and it only grows, in the case I just mentioned, when there's a blue cell there. So that's how you end up getting half a cell per step. Now, it's more elaborate when you get more complicated functions like square roots and things, and you have to just look at pictures. And following my principle, the computational animals are always smarter than we are. When you see one of those that produces some weird algebraic function as its edge, it has basically it's discovered some piece of algebra, and it's often really hard to decode what it's doing, but very interesting to try doing that. There's a question here about cells in the von Neumann neighborhood. That's the 2-dimensional cellular automata. I'll talk about that time after next. That's in chapter 5 of the NKS book. I talk about 2 dimensions and beyond. Okay, Anders is asking about 5 neighbors instead of 3. Well, that's the amazing thing. It is different in detail, but not different qualitatively. With 5 neighbors instead of 3, for example, you can have much more rapid growth because you can grow by 2 cells every step and so on. But you again get the exact same kind of behavior. We could do some experiments here. We'd see that. Again, lots of interesting systems to study. Recently I made some NFTs out of some cellular automata. Those were ones with more colors, but still nearest neighbors. They're just, it's so easy to go out into the computational universe and just find stuff you've never seen before. In fact, we just found some things that just in those kinds of cellular automata, things I'd never seen before just a couple of days ago. Even after all these years, even after more than 40 years of looking at cellular automata, still discovering new stuff, even at this time. Question from Brady about base 10 cellular automata. Don't know. I don't know what there's. I looked at some. They're in chapter 10. There's some towards the end. There's some things about cellular automata that are like that do things with digit sequences like powers of 2 in base 10 and so on. I don't know. I think there's probably some number theory that can be done looking at such cellular automata. One of the things that I've been interested in for a long time is cases like nested cellular automata, where you can plainly see the pattern but you can also study it mathematically. There's the question of, are there methods from number theory, for example, where there are some cellular automata that are sort of exactly solvable cellular automata? We know the nested ones, binomial coefficients mod 2 and so on, those are of that type. The question is, are there other cases where you can have where perhaps some number theoretical function describes the behavior of the system, and you can kind of exactly solve it using the methods of number theory? Never been found. Interesting thing to look for. Okay, Security is asking about chemistry and hexagonal patterns. I'll talk in 2 weeks, I'll talk about two-dimensional cellular automata, and we'll probably talk a bit about cellular automata on hexagonal patterns. I said, let's see. Are there biological analogies, Brady asks, to mobile cellular automata? It's a good question. I think the answer is probably yes. I think, ribosomes running back and forth on strands of DNA, these kind of macromolecular things, they are very much sort of Turing machine mobile automata-like. And I'm now remembering that I think there has been some work done on looking at things like ribosomes and other kinds of sort of editing of these heteropolymer sequences that way. Interesting question. Okay, question from RBS. Are there universal mobile automata like universal Turing machines? And are there mobile automata that are equivalent to Turing machines? Yes, actually in chapter 11 of the book, I think I have examples where I show the equivalence between mobile automata and Turing machines. In terms of what's the simplest universal mobile automaton, very good question. I do not know the answer. Somebody should go find that out. It's a terrific question. That's a quintessential kind of really logical question. I just think collecting kind of the simplest universal system of each type, it's kind of something, you do it now, it'll be that way forever. And it's kind of like, find the simplest universal Turing machine, universal cellular automaton, well, those ones we know, the simplest multi-way Turing machine, universal multi-way Turing machine, the simplest universal mobile automaton, go find it. It's a discovery forever, so to speak. Let's see. David is asking about P versus MP, true but unprovable in set theory. Let me not address that here. I think there'll be things to say about P versus MP and provability in different axiom systems. Actually, my meta-mathematics project that should be coming out in the next week or so, there's some things to say there, although that the whole question of true but unprovability of, or in general, undecidability within an axiom system, unprovability within an axiom system for P versus MP, I think is an interesting one. I did talk about it a bit in the post that I made about post-tag systems. I talked a little bit about that question because I think some of these halting problems of tag systems may have this feature of being, in a sense, unreachable by axiomatic systems like Peano arithmetic or like set theory. Let's see. Parmenides is asking if a universal cellular automaton is a Turing Tarpit. I do not know what a Turing Tarpit is. I should know that. It sounds like my kind of thing. I will have to, I'll have to find out. What is that? Let's see. I'm looking at some definition here. Oh wow. I guess that's a very hard to program in kind of system. I don't think things are as hard to program in as people might think they are. Like my minimal axiom system for Boolean algebra. Yes, I'm a collector of minimal things that do things. The minimal axiom system for Boolean algebra, to prove commutativity of NAND takes 100 steps and it's complicated. But once you have that, it is as efficient as any other axiom system. So in other words, it's quite often the case that there's kind of this layer of kind of stuff you have to get through, getting from the very, very lowest levels of computational structure up to a level that is a little bit more human accessible, but then you're zooming along. And in fact, we see that in metamathematics. I'll talk about this when I talk about metamathematics. And we call it the level of the eames, the atoms of existence that kind of are underneath things like axiom systems and so on. There's this very kind of low level, but once you get above that level, you get more from the sort of molecular dynamics to fluid mechanics. Once you get above that level, then you can start zooming forward. And the fact that you were basing everything on this incredibly low-level structure really doesn't matter anymore. It's just like, we can write Wolfram language and have it do all its wonderful, elegant things, but in the end, it's operating in the machine code of the computer it's running on. There's just a layer. This is something we learn from kind of the whole world of software and practical computing, that you build in that layer, and then you can be much more human and you can go much faster. So I'm skeptical that there really are systems that are sort of truly tar pits in this sense that you always get stuck. My guess is that once you've built that layer, that sort of modularity layer of abstraction, that you can still zoom forward. And I think that's sort of a story, and it's actually something that should be investigated more. That's probably a story deeply connected to the principle of computational equivalence. Okay, I have to disappear soon, but let's just take a couple more questions here. A question from Brady. How do you decide the order of possible neighborhoods for elementary cellular automata with regard to how they're encoded in binary? It's really simple. You're just taking the 111 sequence you're just enumerating the possible sequences, 000, 001, 010, etc. And you're just putting them from right to left. So 000 is on the right, 111 is on the left, and the one is the first one in the number, like rule 30, for example. The first bit there is the result for the 111 step, the 111 the 111 case of the rule. So let me just show you. So if we look here. I think I was looking at it. There we go. There's one. So here it is. The 111 case is over on the right. These are counting down in binary, and that's how these are ordered. Very straightforward. It's one of those things where you invent that in 1 minute and you end up using it for the rest of your life. But it's sort of the obvious way to do it. William asks, does the simplest universal system for each type define a translation distance between languages? Interesting question. It's an interesting issue. What is the significance of the fact that you only go a few tens of cellular automata before you get a universal one, whereas with Turing machines, you go a few tens of thousands of Turing machines before you get a universal one? What is the significance of that? I'm not completely sure. That's an interesting question. Question from RBS, a study of cellular automata with the brickwall neighborhood. Yes, I talk about that actually in chapter 9 in connection with some of the in connection with reversible cellular automata. There's a question here about computational boundedness in biology. I think that's not for today here. Yeah, so that's probably about it for now. I encourage you. You can find all the online NKS book I was showing you. You can find that all online. You can still get a physical book. I'm sure you can still get this from Amazon. Physical books still exist, and there's a hardcover version which I recommend. There's a paperback version which is a bit big for paperback, and the hardcover is really nice. But if you do get the hardcover version, take the dust jacket off. It has a much nicer underneath than the dust jacket. The dust jacket was really intended for life in bookstores, not for life on people's shelves. And by the way, I should say that the online version of the book, we're in preparation for the 20th anniversary, we're working hard to make it so that every image is click to copy, in the sense that you get the Wolfram language code for that image directly there. And you'll find an increasing number of pages, probably in chapter 3, there are many of them, have notebook versions of the images that are there, so you can go and start exploring the kinds of things that are talked about in the book. And well, I think that's it for right now. Thanks for joining me. Next week we'll be talking about chapter 4, which is called Systems Based on Numbers. So we're moving through this book. It has 12 chapters altogether, and we just did chapter 3.